Hi, welcome back to Math 111. We're going to talk today about section 1.6 in your textbook, which is graphs of functions. So we've talked about functions as a particular class of mathematical relations that are characterized by the fact that if you put in one known x value, you get out exactly one y value. And so when we're talking about, and I also talked about the fact that saying something like f of x equals 3x squared plus 2 is another way of simply saying y equals 3x squared plus 2. So hopefully it doesn't surprise you that we can graph functions in exactly the same way that we can graph equations. So if we go to the function definition, for example, and suppose I want to graph this guy, I can pick some x values, calculate some f of x values, and then we're going to graph that. So let's start with x equals -2. If I plug x equals -2 into the function 3x squared plus 2, that means take -2, square it to get 4, multiply that by 3 to get 12, and then add 2 to get 14. If we do this same thing with an x value of -1, -1 squared is 1 times 3 is 3 plus 2 is 5. If x is 0, f of 0 is 2. F of 1 is again 5, and f of 2 is 14. So now if I want to graph this, and let's see, 2, 4, 6, 8, 10, 12. Okay, so 2, 4, 6, 8, 10, 12, and 14. And we're going to call, so this guy is 0, 1, 2, 3, -1, -2. So -2, 14, -1, 5, 0, 2, 1, 5, and 2, 14. We connect the dots, and that is our graph of our function. So what this really means is that every point that appears on that line is a point that satisfies our function. In other words, if for some reason I wanted to know what was the functional output for 1/2, I can estimate that from my graph. All right, let's take a look at what we call a piecewise defined function. So let's try to graph the function f of x, which is defined in this way. It's defined as 4x squared minus 1 if x is less than 1, and x minus 3 if x is greater than or equal to 1. So this function is defined differently depending on where we are on the x-axis. So again, let's start with the table of values. We're going to choose x's, and we're going to calculate f of x's. Let's start with an x of -3. Now -3 is less than 1, so we'll use the top line of our function definition. And it says to take x and square it, which gives me 9. Multiply by 4, which will give me 36, and subtract 1, which will give me 35. That's not a value I'm going to want to graph, but we'll leave it on there anyway. Let's try an x of -2. And again, -2 is less than 1, so we'll use the top line of my function definition. Negative 2 squared is 4, times 4 is 16, minus 1 is 15. And let's try negative 1 for x. Again, negative 1 is less than 1, so we're going to use the top line of our function definition, and we get an output of 3. And I'm just going to fill these in. Now, when I get to 1, 1 is not less than 1. 1 falls under the greater than or equal to 1 line. So now we're going to use the second line of my definition. So if x is negative 1, my function now, or sorry, if x is 1, my function now takes 1 and subtracts 3 to give me negative 2. And if x is 2, we're still on the second line of my function definition, so I get a y of an output of negative 1. And if x is 3, I get 0. So if we graph this, if we want to sketch this graph, okay. So negative 1, negative 2, 1. Should always label your axes so you know what the scale is on your graph. And now we just plot our points. So the negative 3, 35 and the negative 2, 15 are not on my grid, but negative 1, 3, if x is negative 1, y is 3, that point's about here. If x is 0, y is negative 1. If x, okay, and so let's talk about where this function comes close to on that top line. So let's say I plug in x is 0.0, oops, sorry, I want to get really, really close to 1, so 0.9999. Let's use my Desmos. 4 times 0.9999 squared minus 1 is almost 3. So what that tells me is that if I could plug in a value of 1 to this, it would be at 3. So what I do is I put an open dot there because I need all of these values up until 3 to be defined. Okay? And let's try that again because I missed my 3 point. There we go, that's better. Okay. But now, the actual value when x is 1 is negative 2, so we put a closed dot down here. And if x is 2, y is negative 1. If x is 3, y is 0. And this is just going to make a straight line that goes through those dots. Okay. And that's a graph of this piecewise defined function. Okay, so there's a basic explanation of graphing functions. A couple of things we need to be aware of is that we can look at the graph of a function to talk about the domain, because remember the domain is all of the x values that for which a function is defined. Well, that's also the region of the x-axis over which we can graph the function, right? And the same thing about the y, except the y is related to the y-axis. So we are going to talk a lot about the zeros of a function. And the zeros of a function are the x values where the function output is 0. In other words, they are the solutions to that equation, to the equation f of x equals 0. They are also the x-intercepts, because the y-coordinate of every x-intercept is 0. So for these two functions that we just worked with, this function, this piecewise function, has a few zeros. It's got a 0 here, and here, and here. Okay? And we'll talk about how to find those zeros. In fact, we can find them now. So for this function, if we wanted to find its zeros, we need to solve the equation f of x equals 0. And because this is a piecewise defined function, that means we're looking at a solution to 4x minus 1 equals 0 and x minus 3 equals 0. Solving the first one, we add 1 and we get 4x squared equals 1. We divide by 4 and we get x squared equals 1/4. Take the positive and negative square root. Square root of 1/4 is 1/2. And those are these two zeros. So this function has a 0 at negative 1/2, 0, which is that point there, and at 1/2, 0, which is that point there. Now to solve this other one, it's pretty simple. X equals 3. So our third 0 is at the point 3, 0. So this function, again, has 3 zeros. 1/2, 0, negative 1/2, 0, and 3, 0. Okay. We're going to talk next about testing a function for symmetry, but I'm going to do that in a separate video, so I'll talk to you again soon.